Dear students, Assalamu alaikum. This is the fourth program on Software Engineering 1 course. In the previous two programs, we discussed what is software process. Software process basically defines the major activities which have to be carried out to develop a software. Of course, we presented different process models. They were different in their phases. Some of the models have some good points and also they have some negative points. But there is no good model as such. It is the judgment of the software engineer that whenever he wants to develop a software, he has to decide that which process model is suitable for developing that software. Once the software is developed, of course, the software in its own is useless. It has to be combined with processor on which it will run and some other hardware to make it a system. Also, software is not an independent entity. Think about all the modern gadgets we have today. The mobile phone you have, the automatic assembly plants, even the aircrafts, all these systems are run on the software. Therefore, the software engineering cannot be treated in isolation. Software engineering has to be treated as a part of even a bigger spectrum, what we call the system engineering. Today's program is about system engineering. We'll define what is system engineering and how the software engineering fits in a bigger picture. The objective of our today's programs are, we'll define a system and also what is system engineering. We'll explain what is system engineering hierarchy. We'll also explain system engineering process and some of its related issues. And we'll explain the system design process. So let's start by defining a system in general. A system is defined as a purposeful collection of interrelated components working together towards some common objective. In the context of software engineering, of course, we are not concerned with the systems in general. We'll be focusing on those systems in which the computer hardware and the software is used as major components. So we are interested in the computer-based system. A computer-based system is defined as a set of arrangements of elements that are organized to accomplish some predefined goals by processing information. Dear students, you might have noticed something in both of these definitions. The first important thing which is mentioned in the definition that the system is made up of some elements. These elements don't just work independently, but they have to interact with each other to achieve a common objective. For example, the goal of a system may be to support some business function or to develop a product that can be sold to generate business revenues. What is important to note in both of these definitions is the fact that different elements of a system interact and work together towards achieving a common objective. A system cannot be made by just putting different elements together which don't work together towards a common objective. For example, the goal of a system may be to support some business function or to develop a product that can be sold to generate business revenues. To accomplish a goal, different systems may have different elements. For example, the elements of a computer-based system are software, which are basically the programs, hardware, people, databases, documentation, and procedures. These are the common elements of a business information system. These elements interact in a variety of ways to transform information. Each element of a system may have its own properties and behavior, but when these components are brought together and evolve as a system, their behavior and properties may change. These properties, which emerge out of the combination of these components, are generally called as the emergent properties. These emergent properties cannot be attributed to its component. Yes, systems do maintain some of the properties of its components, but system as a whole also has some properties which cannot be inferred from its components. The emergent properties of a system may be functional or non-functional. The functional properties appear when all parts of a system work together to achieve some objective. For example, a car has different elements, such as it has an engine, tires, gears, etc. Each element having its own properties and its behavior. But when these components, these elements are brought together to make it a system, that's a car, then the function of the car is to take you from one place to another place. That emergent functional property cannot be derived from its elements. You cannot take the engine and say the engine can take you from one place to another place unless all the elements are put together. The non-functional properties relate to the behavior of the system in its environment. Every system has to run in some environment. Some examples of the non-functional properties are the overall weight of the system. Of course, the overall weight of the system can be derived from its components, from the elements of the system, the weight or the size. If we are talking about a pure computer-based system, then the size of the total software can be derived by summing up the size of each element that makes up that software. Another example of the non-functional requirement is the reliability of the system. Dear students, different elements when taken independently may have different reliability. The components may be very reliable, but once those components are put together as a system, then one could not be expecting that all those components will be showing the same reliability. A lot of problems are discovered when these components interact with each other. This interaction may negatively affect the reliability of the overall system. Another non-functional property of the system is the usability of the system. Each component might be easy to use or it might be difficult to use. But when these components and these elements are brought together in the form of a system, then how easily the system can be used depends on many factors. For example, how well these elements are hidden behind the interfaces, how much interaction of the user is required with the elements. Of course, a system where the user has to interact with the overall system as a unit will be much easier to use as compared to the system in which a user has to interact with its individual components. A system hierarchy defines a system with its subsystem in a top-down manner. Let's explain it with the help of a diagram. We have a business or a product domain. The word view specifies the overall functionality of the business. Within that domain, it might have some subdomains, what we call the domain view or domain of interest. Then each domain has its own system elements, or the subsystems, and then each subsystem can have its elements, and these elements can be again defined in its details. For example, a manufacturing system has various domains of interest, such as production, procurement, sales, finance, etc. Each domain in itself is a system. Each of the domain has its own subsystems, which may have their own subsystems. For example, one of domain of interest is the production system, which has robots, numerical control machines, data entry devices, etc. as its subsystems and so on, until we reach to the level of the hierarchy where dividing a subsystem into subsystem doesn't add anything into the understanding of the system. Note that each system and subsystem is a system in its own right, whether it's a robot, it's a numerical control machine, or a data entry device. It has its own elements, such as hardware, software, people, and so on. The following figure illustrates yet another very familiar system. This is a system of a town which has streets, and street itself makes a subsystem of the town. In each street, we have buildings, and inside building, we might have a number of other subsystems. Each of the system and subsystem at an outer layer in our second example are up in the hierarchy or at the same level of the hierarchy makes the environment of the system. Dear students, environment is very important from the software engineering point of view. As we explained before, software is not an isolated entity. It has to work within its environment. Therefore, it is the work of the software engineer not to only understand the functionality of the software itself, but also understand its environment in which it will be ultimately operative. We have explained that the system is made up of elements. These elements work together to accomplish a common objective. Also, a system may have subsystems of another large system. All that makes system development a complicated and difficult undertaking. Therefore, it is important to use a disciplined approach in designing and building a complete system. System engineering provides us with such a framework which can be used to analyze, design, and materialize a complete system. Formally, system engineering is defined as designing, implementing, deploying, and operating systems which include hardware, software, and people. Our definition of system engineering is specifically for the computer-based systems. Since system engineering is a very complex undertaking, it has to be carried out according to a well-defined process. As we discussed in relation to the software engineering itself was a very complicated process. Therefore, we discussed various models which can be used to develop a high-quality product. When we are considering even a bigger scenario of developing a complete system, we cannot escape from a process. A commonly used system engineering process model is shown in diagram. Similar to software engineering waterfall model, system engineering process model is also divided into a number of phases. The first phase is requirements definition. The second is system design, subsystem development, system integration, system installation, system evolution, and system decommissioning. The waterfall model of software engineering was basically derived directly from this model. However, there are some important distinctions between the system engineering process and software engineering process we should be looking at. These are interdisciplinary involvement. A system is not made up of only software. So we cannot think that only the people with the software engineering background should be involved in developing a complete system. System engineering is an interdisciplinary approach. Engineers from different disciplines have to work together. And we know when the people with different background are brought together to work on a single project, there is a lot of scope for misunderstandings. Different engineers with different backgrounds speak different terminologies. They have their own ideas. They have their own ways of visualizing the thing and implementing the things. So when these people with different backgrounds are working together, they should be careful to avoid misunderstanding or to develop a mechanism to resolve the misunderstandings so that the end product is a quality product. Another distinction is that there is a little scope for iteration in the system engineering. Hardware changes are expensive to make. Therefore, system redesign is often impossible. Problems which may arise have to be solved within each subsystem rather than changing the whole system. Many a time, software may have to compensate for the hardware problems because redesigning the hardware and developing the hardware again is very expensive. So the people tend to resolve those problems with the help of software. Dear students, let's go back to the system engineering process and explain it in a little more detail. The first step of the system engineering process is the requirement engineering or the requirement definition. Similar to the software engineering, system engineering starts with getting the user requirements. Every system which is built for some use. It has the users. Therefore, the first activity which has to be carried out in the engineering discipline is the communication with the users, communication with the customers, and trying to find out that what the system should be doing for them. Requirement definition phase usually concentrates on driving the three types of requirements: coarse-grained function requirements, system properties or non-function requirements, and undesirable characteristics. The coarse-grained system requirement define the basic functionalities of the system in an abstract level rather than in detail, since detailed requirement specification takes place at the subsystem level. System requirements is not an easy task. There are many problems one has to face and tackle. The common problems are changing as the system is being specified. Like software, users are generally not fully aware of their requirements. That was one of the reasons we use the prototyping, so that we can get a complete picture of the user requirement. And when we are working at the system level, getting all the user requirement is very painstaking business. Not only that, but with time, the user keep changing their requirements. They keep giving you the new requirements. Therefore, one has to accommodate those new emerging requirements. Some mechanism has to be devised to control the requirements and the changes in the requirements. We cannot keep going and keep changing the requirements forever. There has to be a cutoff point after which we should not be taking any more changes in the requirement. The another problem with requirement definition is must anticipate hardware communications development over the lifetime of the system. A system is designed and developed for a larger time span. Therefore, as a system engineer, it is the responsibility that we should be looking into the future requirement of the business. We should be looking at that what technological changes will take place in the future so that we can accommodate for those changes in today's system. Otherwise, after some time when the hardware and the software changes, our system will become obsolete and it has to be taken out of the function. Another thing is how to define non-functional requirements. Generally, users know up to an extent that what their system should be doing, that means the functions of the system, what they are expecting out of the system, what processing that system has to do, and what information it should provide to the user. But defining the non-functional requirements are very difficult. Non-functional requirements include, for example, the reliability of the system, the efficiency of the system, user-friendliness of the system, and similar other aspects of a system. The second phase of system engineering is the system design phase. System design phase is concerned with how the system functionality is to be provided by different components of the system. As we discussed before, a system has subsystems, and each system in turn has its elements like people, hardware, and software. So during the system design phase, we have to decide that what are the functionalities of each subsystem and how those functionalities will be realized by either hardware, software, or by other elements of the system. System design is itself a complicated process that we'll be discussing in our next program. Dear students, in today's program, we defined what is a system, we discussed what is system engineering, and how the software engineering fits into a bigger framework of system engineering. We also explain that system engineering itself is a very complicated process that has to be tackled in a disciplined way. In that regard, we presented to you a system engineering process model, which is basically a waterfall model. We discussed the first phase of that process model, that how the requirements are gathered or what are the basic points in the requirement definition phase. We also defined that what are the objectives of the second phase, that the system design phase. In the next lecture, we'll continue from this point and discuss the remaining phases of the system engineering process. With this, we come to the end of this program. Allah Hafiz.